Hello, everyone. In this video, I want to show you how to solve USAPhO 2021 Problem B1. This problem gives us the following physics system that consists of two objects. One is a disk with uniform mass density. The total mass is capital M. The radius is R. And there's another small mass, right? An n of mass, yeah. Small m that is much smaller than big M. Okay, so this problem has two parts, and for both of these two parts, the common thing is the end actually moves on the disk. Okay, so it has some trajectory, and because of its moving, so it leads to the rotation of the big disk. So this problem asks us to study that for different moving trajectories, then how it leads to the rotation of the disk. Okay, or what is the angular displacement of the disk after the end completes its walking? Okay, all right. So because these two parts, share some common features, right? But the only difference is that so they have different ends moving trajectories. So what I want to do here is to first to derive the result and write it in the general form. And after that, I will plug it specifically into each of these two parts and to get the specialized results for these parts. Okay. So first, let's look at this problem in a general way. Okay. So let's think about it. Why the move of the end leads to the rotation of the disk? The reason is because you look at these two as a whole system. There is no external force. So the system's total angular momentum is conserved. And when we say the total angular momentum, the reference point that we choose, so naturally we should choose the center of the disk, right? So in the rest of analysis, let's choose the center of the disk as the reference point. And about this point, the system's total angular momentum is conserved. So we will use this fact to write down the following equation. Okay. All right. So because we are doing analysis on the disk, it would be easier for us to use the polar coordinate system, or in the 3D space, we call it cylindrical coordinate system. Okay. So let's say, suppose the angular displacement of the disk at time t is denoted as theta sub t. Okay. And we assume that for the end, its position is denoted as r sub t. Okay. All right. So now we have the following equation about the conservation of the system's angular momentum. So here, when we talk about the angular displacement, so it would be good if you treat it as a vector, so it has a direction, right? So the vector we choose, suppose theta is in this counterclockwise direction, so basically is the z direction, right? So the z actually goes out of my screen, okay? All right. So the angular momentum of the disk, suppose let me use I to denote a moment of inertia about an axis that is in the z direction and that passes through the center of the disk. Okay. And the angular momentum of the end is equal to its mass times its position, cross product is velocity. So this is always 0. Okay. All right. So by taking the integral and assuming that the disk's initial angular displacement is just a 0, okay? Then we get the following formula. So delta t is equal to m over I times the integral over time, right? So integral over time. Yeah, so here we already have t, so let me use s to denote the time. Okay. All right. And for the disk, because its mass is uniformly distributed on it, and we know its radius is capital R, so we can easily compute its momentum of inertia, right? So it's simply equal to a half of its mass times R squared. So if you plug it to the equation above, it is equal to okay. So this is the general formula about the disk's angular displacement. Okay, so next we apply this formula to each of these two parts and to get the specific answers. Let's first look at part A. So this is the moving path given in the problem, okay? So this is called theta, right? The problem name is at theta, whatever. So this is different from the theta we use above, but this is something, yeah, whatever. So this is the moving trajectory, okay? So let me separate them into 4 segments. Suppose here we move in this way. This is 1, this is 2, 3, this is 4, okay? So the central thing is to compute this integral, okay? So we have to do it on each of these 4 segments, okay? All right, so it's not so easy to directly do this integral over the cross product. But for this particular path, actually, if we use this pattern, it could simplify our analysis a lot. Let's look at this pattern, what it tells us. Well, so for path, first let's look at path 1, okay? So path 1, we observe that we keep the distance between the end and the center of the disk to be the same. So that being said, for path 1 and 3, we have an important feature that the velocity is perpendicular to the position. So the cross product is simply equal to the product of these 2 numbers. That's it, right? It's very elegant. And the next, let's look at the direction of the cross product vector. So let's first look at 1, okay? So for RS, right? We know for these 2 parts, so they're always in the radial direction, right? So for path 1, RS is equal to R ER. So for path 3, RS is equal to R minus H, where we know. So this small part is H, right? Times ER. And on path 1, what about the velocity? So let me assume that the angular displacement for the end reference to the center of the disk, okay, is called, let's say, alpha, okay? of the end. It's called alpha. So because for trajectory 1 and 3, so it moves in the tangential direction. So it is equal to the radius times EV. Okay. And for path 3 is equal to the radius r minus h times c. Okay. So those are about paths 1 and 3. And next, let's compute their integral. So for path 1, what is integral? So we take out r squared. And let's look at the cross product of the unit vectors in the cylindrical coordinate system. So rs dot is E phi cross product ER is equal to negative of z. Right? Okay. Oh, my bad. So there's one thing I missed here. So here for the velocity dot, so it is alpha dot. Here's alpha dot. Okay. And then we just integrate over alpha s dot. So the total angular displacement on path 1. Suppose we treat the counterclockwise rotation as positive. So because path 1 is clockwise, so it's negative theta. Okay. And then let's look at path 3. So pretty much the same thing. So we replace r with r minus h. The integral alpha s dot ds. And for path 3, so our angular displacement is in a counterclockwise direction, so it's positive theta. Okay. All right. And then we have to take such integral for paths 2 and 4. But for paths 2 and 4, we have the following observation. So we move in the radial direction, right? So it means that rs dot is parallel to rs. Therefore, it implies that their cross product is 0. So you take the integral, it's just 0. It's fairly simple, right? Okay. By putting everything together, we get a result for the total angular displacement for the disk theta t. Okay. So we just sum over the integrals over 4 segments. So we just have the first one and the third one, right? That gives us z times, right? So let me divide r squared in each term in the parentheses, okay? You get this one. And recall that this problem assumes h is much smaller than r. So we can apply the formula that if x is close to 0, it's approximately 1 plus in x. So you plug it here, then this result is approximated by this one. So this is the answer to part 1. All right, then let's apply this general formula to solve part B. Okay. We call this is the disk's total angular displacement. So we have to find out the value of this integral for this new path. So the new path is a circle, right? So how to do it? Well, so we have to exploit its feature. So probably the best way to characterize the position of the end is to use the following way. So let's characterize this by using the sum of two displacement vectors. So one is here. The displacement from the center of the disk to the center of the end's trajectory, right? Because we know that regardless of how the end moves about this small circle, so this red vector never changes, right? So let me call this vector as capital R. And then by using, so let me call this point A as the new reference point. So the end is making a circular motion, right? So the way to characterize its circular motion is to use the cylindrical coordinate system for this smaller circle, right? So let me introduce the coordinates in this way. So about this new smaller center A, so let me use rho t to denote the position of the end about A, okay? And let me use this angle, say phi sub t, to denote the angular displacement on this small circle by the end, okay? So you see that we introduce this blue smaller coordinate system, so it becomes pretty easy to characterize the position and the motion of the end, okay? And then we will use this particular coordinate system to take this integral, okay? All right. So for this integral, what is Rs? Rs is essentially R plus rho t. So its velocity is, we check the dot for each component. Oh, let me take S. Yeah. Actually, this is very easy because capital R never changed. So its dot is just 0, right? So the above integral can be simplified as this one. And for this, recall that we have two terms in the parentheses. So let me separate them and take the integrals for each term respectively. For the first integral, because capital R doesn't change over time, so we can take it out of the integral. Okay. And let's look at the first blue integral. So rho s dot ds, it is equal to the displacement from the end's initial position to its final position. And recall that this part says the ant makes the detour. So finally, it goes back to its original position. So this is simply equal to 0. Therefore, we just need to take the second integral. What about the second one? The black one. So recall that the ant is moving on a small circle. So by using that as a reference frame, because rows of S is defined by using that reference frame, right? So rho S dot is in the tangential direction, is always perpendicular to the radial direction, right? So this can be written in the following way. So rho S, the radial length is R, so times phi t dot, as its direction is tangential, so is, let me call it EV, okay? Cross product rho S is R ER, right? So their cross product has direction negative Z. And the value is R squared phi t dot. Oh, so we use time S. Yeah, let's do S. And then we just take this integral over phi st, right? So then we get is angular displacement. So by rotating for a whole circle, the angular displacement is just the 2 pi, right? So by putting the above analysis together, then we get the first term is 0. The second integral is negative Z times R squared times 2 pi. And by doing some simple algebra, we get the final answer. So this is the solution to this part.